Well, hello everybody, Dave here, and we are now going to do the third lesson in a series of lessons on this idea of sampling distributions. Hopefully you've watched the previous two lessons where we talked about dealing with sampling distributions of sample proportions and the definition of what a sampling distribution is and exactly what conditions we need to satisfy in order to use a normal distribution to approximate this sampling distribution that we're going to create. So when we have quantitative data, what we're going to end up doing is finding a statistic that's going to be a sample mean. So if you remember from the first lesson, we were talking about statistics to mean. After we've been given a sample, we calculate whatever it is that we're trying to create a sampling distribution of, whether it be a sample proportion, a p hat, or in this case, a sample mean, x bar. And so we have here two distributions. We have one that's a population distribution of household earnings, and then on the right we have a distribution of the mean household earnings. Now, this is a very clear signal that we're looking at a sampling distribution on the right because they're specifically talking about the mean household earnings for samples of size 100. So you can imagine taking a sample out of this population on the left of size 100, finding the mean household earnings, and then plotting it on this particular set of axes. Now, when you look at it, you can see two things are abundantly clear. When you look at the population distribution on the left, you can see that this thing could arguably be skewed to the right. And you can see on the diagram, they've actually indicated where the mean is. However, when you take a look at the sampling distribution on the right, you can see that this looks approximately normal, certainly symmetric at minimum, and with conditions satisfied, we could certainly argue that it is approximately normal. But you can also see that this sampling distribution is also centered at the same location that the population distribution is. Now, this is an interesting result because now you can see that the shape of the sampling distribution does not have to be reflective of the shape of the population distribution. This is going to be an important understanding moving forward. Just like we did with sample proportions, we could also do the derivations for what the mean of the sampling distribution is and what the standard deviation of the sampling distribution is. But I think instead you've gotten the point that we're going to imagine that we're taking a set of random variables x and we're going to perform a transformation of the calculation from the original discussion of means and standard deviation of means that we've had in chapter 6. So I would just go back and take a look at that yet again. But much like with 7.2, we end up having a relationship that clearly shows that the mean of the sampling distribution, which we'll write as mu sub x bar, has to be approximately equivalent to the parameter of interest, which in the case of having quantitative data is going to be the population mean, represented by the Greek letter mu. When we calculate the standard deviation of the sampling distribution, we simply need to take the standard deviation of the population and divide it by the square root of the sample size that we've selected. Of course, as with all distributions in all usages of binomial distributions, we can only do this if the 10% condition is satisfied because, of course, we're playing around with this idea of independent samplings. Now, one thing I do want to point out as something that we're going to see down the road, you'll notice that to calculate the standard deviation of the sampling distribution for x bar, you actually do need the standard deviation for the population to do so. The question would probably arise, well, what happens if you don't have that, as most studies tend to not have a standard deviation from previous study? We do have a situation where we can deal with that, but I do want to point out the fact that you do need the standard deviation in this case, but in the proportions case, we were actually able to calculate it knowing the population proportion and the sample size on its own. So an interesting relationship to consider when you're reading the scenarios in given problems to try and figure out what kind of test are you exactly doing. But now I want to talk about the sample size itself and the idea that when we are sampling from a population, is there anything that we can say about the shape that may be interesting for us moving forward? Again, I think we've all picked up on it by now that in this chapter, the whole goal is to take a particular scenario and try to use the normal distribution to describe the sampling distribution. But of course, in order to do so, we have to satisfy three conditions to do so. Now, there's going to be a couple of different situations to consider with sample means. The first is if you are given information that the population is normally distributed. And if that's the case, life is good. Because if we know that the population is normally distributed and they will outright state that it's normally distributed, well then we can already immediately go to using the sampling distribution with a mean that is approximately equal to the parameter of interest and the standard deviation of that sampling distribution equivalent to sigma over root n. Now, of course, the other conditions have to be satisfied in order to use that center and spread. However, when it comes to shape, if it's stated to be normal in the population, then regardless of sample size, we will be able to assume that the shape of the sampling distribution is normal. But what happens now if we have a distribution that's not normal, like the original example that we had? Well, that's going to make things a little challenging, and this is where we really have to try and understand the concepts behind this. Now, when we are creating a sampling distribution, there is in no way an expectation that that distribution is supposed to look like the population. Simply put, we are trying to find the center of the population. That is the parameter of interest by which we are trying to create a statistical study to discuss whether that center is what it should be or if we should maybe consider a different value. But when we have a non-normal distribution, how do we select a sample size such that we will always, or at least can assume to always get this normal distribution? We just said in the previous slide that if the population is normal, we just get to assume it's normal regardless of sample size. But as we've seen throughout the series of lessons in the last couple of chapters, that there will definitely be a sample size by which you will see this distribution of the sampling distribution start to converge towards this idea of being a normal distribution. And there is an amazing theorem known as the central limit theorem in statistics, and I consider this as true to nature as the sky is blue. And it is something that is a fundamental principle within the realms of statistics, and it basically says this: when we are taking independent random samples from a population, so long as we have a sample size that's greater than or equal to 30, we can readily assume that the sampling distribution of the sample means will be approximately normal whether the population is or not. Now that's an incredible achievement, because in the first case, we just said if the population is normal, the sampling distribution will be normal. I think logistically that makes sense. But the idea is no matter what the population looks like, so long as we select a significant sample size, and I've already alluded to the idea that 30 is going to be that magic number, then we can assume that the sampling distribution itself will be approximately normal too. I do want to come back to this original statement that the sampling distribution is in no way supposed to replicate the shape of the population. However, in the case where it's normal, it will. But in non-normal cases, so long as the sample size is large enough, we will get a normally distributed sampling distribution. Now, there is one thing that I want to point out when we discuss this, and it's this idea of a finite standard deviation. That sounds a little counterintuitive, but I want you to think about what we are doing in this chapter. We're taking a binomial distribution, a discrete binomial distribution where we have countable things. We are creating essentially histograms, and as we collect more and more data from more and more sampling, we see this distribution begin to grow and approach the shape of normal. And because of that, we can readily approximate that binomial distribution as a normal. There are other distributions that exist within statistics. The most obvious one is one called the Cauchy distribution, and I will leave that for another teacher in another course in another year to describe what that is, but that's actually coming from a continuous probability distribution, whereas when we're dealing with things that are countable and measurable, we're referring to that as a finite case. And so independent sampling has always been the necessary evil when it came to dealing with approximating a binomial distribution as a normal distribution, but now on top of that, this finite standard deviation, which is just purely by the nature of what we're doing in a study, is a requirement to invoke the central limit theorem. The one thing I do want to point out, though, is that this is specifically for the cases when the population is non-normal. If the population's normal, the sample size is irrelevant to the shape. We know it will be a sampling distribution that's normal. But in the case of the non-normal distributions, we may have to invoke the central limit theorem to approximate that distribution as a normally distributed case. So let's take a look at this in action. Here is a population distribution that is wildly non-normal, and there are simulators online that can allow you to play with this, and I encourage you to do so, and especially when you start playing around with sample sizes, because look what happens when we increase the sample size. This is a sample size of 2. So if we had a sample size of 2 and the population was normally distributed, then this sampling distribution would begin to approach a normal distribution. But in this case, it's pretty clear it's not doing very well. If we have a sample size of 5, you can see already we're starting to get a shape that is starting to look normal. Now, I do want to warn you that this particular shape is going to have a very specific name later on, and it is certainly not going to be a normal. You can tell that by how thick the left wing and right wing are. So it's important to not look at symmetry and think that it's normal. We're going to be looking at the sample size instead. You can see from 10, it's really starting to have that single peak distribution. And then at 25, you can really begin to see how you have that empirical rule style of the data distribution from the center out 1 sigma, 2 sigma, and 3 sigma. And so in some realms, 25 will be that magic number for the central limit theorem. I've always erred on the side of caution and said that 30 is. But regardless, you can see with a distinctly non-normal population, as you increase the sample size, you converge on this shape that is approximately normal. N equals 5 and N equals 10, those two are not normal, but as we will learn in future chapters, that's known as a t-distribution. So if we have a sample size that's a little larger than 25, where 30 again is that magic number, it doesn't matter what the population distribution looks like. We will have a sampling distribution that is approximately normal with an unbiased estimator and a spread according to the other conditions that we need to satisfy, which of course is random sampling and the 10% condition. And so this particular slide here is super important because it's showing you when you use the central limit theorem and when you don't. When the population distribution is normal, sample size doesn't matter. We can use the normal distribution to approximate the sampling distribution. When the population is non-normal, then we can invoke the central limit theorem. There's also the case, of course, where we don't know anything about the population, but in this particular section, if we don't know anything about the population, then we also wouldn't know the population standard deviation, and that leads us down a different road. Stay tuned for that at a later date. So if we take a look at the image, you may have recalled this from 7.2, but again, we have a population. We take samplings of the same size n out of the population. We find the statistic, which in this case is x bar. We graph all the x bars that we get on the horizontal axis, and from this you can see clearly that the distribution is beginning to grow to the point where it is approximately normal, with a center equivalent to the parameter of interest, which is mu, and a standard deviation that is related to the population standard deviation, but of course is more so related to the sample size. You will remember from previous studies that as the sample size grows, the standard deviation of the sampling distribution should shrink, and this representation of the standard deviation still represents that exact relationship. So that's an important statement to understand moving forward. If we do an example to kind of tie this all together, we're now going to hear things that sound like population but actually means the sampling distribution, and in other cases we may have to actually try to understand how to interpret it. But in this case, we have an example where we're talking about chocolate bars in a machine. They tell us a mean and standard deviation. They tell us that it is normal. That's important. That means we can immediately go to the fact that the sampling distribution is normal when we need to calculate it. But what we want to find out is the probability that the weight of a randomly selected candy bar is less than 7.85 ounces. So they told us that the population is normal, so I can get right to the point and calculate a probability that the value x is less than 7.85. And of course, we use our typical normal CDF with the lower bound, upper bound, and mean and standard deviation as listed. This is very classic basic calculations using the normal distribution, and you get a value of 0.0062, which is not incredibly high, absolutely. You'll notice again that the notations are absolutely vital. You'll notice I've not satisfied any conditions because this is not a sampling distribution. We are using the population distribution that has already been told to us to be normal to find this probability. B, on the other hand, is a slightly different question because now, instead of dealing with the population distribution, you can see that they've now invoked this sample size. They're saying, okay, 4 candy bars are selected at random and their mean weight x bar is computed. Describe the center, shape, and spread of the sampling distribution of x bar. So it's right in your face telling you that you have to talk about the sampling distribution. And as soon as they tell you to do that, you have to focus on the conditions first. Because if we're going to calculate a sampling distribution, then it has to be an unbiased estimator, which means random selection has to have taken place. It has to be independent sampling, which means the 10% condition must be satisfied. And in our case, because we're dealing with sample means, we're going to check something called the large sample condition. Now, in this case, we don't need a large sample because the population was stated as normal. So regardless of the fact that we're dealing with a sample size of 4, we can assume that the sampling distribution will be normal because the population was normal. Once you have all those done, now we can discuss the center and spread because we know that if everything is done appropriately for a sampling distribution, then the center of that sampling distribution should be equivalent to the parameter of interest, which is 8.1 ounces. But here's the big one, and here's the one that students will mess up a lot. When we want the standard deviation of the sampling distribution, we have to calculate it using the equation sigma over root n. If you use the standard deviation that's given to you in the question, well, that's the standard deviation of the population. We are no longer discussing the population. We're discussing the sampling distribution, so you have to calculate it. And so this was one that had a nice answer of 0.05 ounces. Please also note, of course, that now that we're not dealing with proportions, we are dealing with means. These values have units. Please include those units in your discussions. When it comes now to finding the probability that the mean weight of the 4 candy bars is less than 7.585 ounces, you can see now from the notation that I've changed it a little bit. Instead of the probability that x is less than 7.85, it's the probability that x bar is less than 7.85. And again, we use our typical normal CDF because we've justified the use of a normal distribution for the sampling distribution. But you can see now that the standard deviation is the big change. It's now 0.05, not 0.1. I would encourage you strongly that everything that we've done previously up till now when it comes to why we calculate the standard deviation, why we don't, why the notations matter, all those things, that's super important. One obvious exception you may notice is that I haven't been standardizing the quantities right now. You could technically do so, but in this case, I'm showing you the difference between the population and the sampling distribution calculation. But you can see here that we have an outlandishly small number. I would probably write that in scientific notation, but I'm writing it down to show you that it is a whole lot smaller than the previous question. This leads us then to an obvious comparison of why are they different. And this is an important interpretation to understand, is when we're taking a random sample from the population and we're just finding one chocolate bar, well, what these answers are saying is that the probability that selecting one chocolate bar at random that's underweight is going to be a lot larger than if you take a sample of 4 and find the mean weight to be underweight. And so it literally is understanding what calculations you're performing and what those numbers represent. So I would encourage you strongly to understand the difference between a random singular sample from the population versus a creation of a sampling distribution and understanding how that sample size plays a role in the discussion of the values. And finally, and perhaps the best way to wrap up this entire section, is to understand what happens now if we find out that the population is indeed distinctly non-normal. We've already gone through the process of saying that the shape of the sampling distribution is normal because the population one is, and that's fine regardless of sample size. However, if it's distinctly non-normal, we're in trouble because the only way that we can assume that the sampling distribution is normal is to have a sample size that's sufficient enough to say so. And again, we've set that benchmark at 30. We can see that we have a sample size of 4, which means we can't invoke the CLT, which means we cannot assume that the sampling distribution is going to be normal in shape. That means that we're going to have to do much harder math to get the answers that we require. And so that's going to be a different lesson for a different year. For now, just understand that when you see that sample size, if it is not large enough, if we end up with a population that's non-normal, we can no longer assume that it's normal because we do not have the ability to use the CLT. So folks, that's the end of chapter 7. And it's a big one because it's the culmination of the previous 6 chapters of understanding. And now we have the final tool. We have the final piece in place to be able to really make some important significance testing and significance conclusions based upon some real statistical calculations. So next up, we're going to start applying all the stuff that you've learned up till now. So I would encourage you, if you're shaky at any of this content, go back and start restudying because you're really going to need that understanding moving forward. Best of luck to you with your studies, and we'll see you again.